Hi, everyone. So in this presentation, I'll talk about how to convert a wide range of manual memory reclamation schemes into automatic reference counting. And this is joint work with my collaborators, Daniel Anderson from Carnegie Mellon University, and also my advisor, Guy Bullock. So on the conference program, this paper is listed under the old title, Is it Time to Retire Manual Memory Reclamation? So if you came for that talk, then you're in the right place. So it's well known that concurrent programming can be very tricky. And at the same time, it's also necessary for many kinds of parallel applications, such as parallel schedulers, operating systems, and also any data structure that gets shared across multiple threads. So one of the biggest challenges to doing concurrent programming is figuring out when it is safe to free a piece of memory. And this is known as the safe memory reclamation problem. So to see an example of what happens, suppose you have a concurrent linked list, and the node C gets removed. In the sequential setting, you can usually free C's memory right away. But in the concurrent setting, there could be other processes that are just about to access it. So you have to sort of detect these other references and wait until they're destroyed before you can free it. So solutions to this problem can be broadly broken up into three different categories. There's manual SMR, concurrent reference counting, and garbage collection. And there has been a tremendous amount of work in each of these three categories. So also, these categories aren't mutually exclusive. So for example, some garbage collectors also use ideas from reference counting as well. But for this talk, we'll focus on implementing reference counting in the non-garbage collected setting. But some of the ideas here could be useful in the garbage collected setting as well. Okay, so in practice, concurrent reference counting has been gaining in popularity. So for example, it's been recently included in the C++20 standard under the name of atomic smart pointers. So each of these approaches comes with their various advantages and trade-offs. And in general, as you go from left to right in this diagram, the techniques become more automatic and easier to use. So for the rest of the talk, I'll focus on comparing manual SMR to concurrent reference counting, assuming that there's no automatic garbage collection. And in this setting, reference counting usually results in shorter and simpler code, and it's also less error-prone. And in contrast, for manual SMR, we've seen lots of bugs related to improper use of those techniques. So however, the disadvantage of reference counting is that its state-of-the-art solutions are still quite a bit slower than the fastest manual SMR techniques. And sometimes the gap can be as large as a factor of 2. And also another weakness is that reference counting isn't able to automatically collect data structures with reference cycles. So our work aims to address both of these limitations. We shrink the performance gap by quite a bit, and we also implement a special type of pointer that helps with reference cycles. So to shrink the performance gap, we describe a recipe for converting manual SMR techniques into reference counting techniques. And as a concrete example, we show how to take state-of-the-art manual techniques like hazard pointers, APOC-based reclamation, and Hayline, and convert them into reference-counted variants. And the speed of these reference-counted variants are usually within around 15% of the manual techniques that they are based on. So the second contribution is an implementation of weak pointers that supports concurrent accesses. And weak pointers essentially allow you to write data structures with cycles in them and still have it be automatically collected. And there's many existing implementations of this, but to the best of our knowledge, there's only one that supports concurrent operations. And the algorithm that we present here is several times faster than it. So implementing weak pointers efficiently involved first implementing a primitive that's called increment if not 0. And we present the constant time algorithm for this primitive, which could have applications to other problems as well. And finally, we implemented all of these ideas as a C++ library and experimentally compared with existing approaches. And I won't have time to cover all of this in detail, so I'll focus on just the first result and then go over some experiments for it. So our work builds a lot on existing manual SMR and reference counting techniques, so I'll go over those to start. So the defining feature of manual SMR is that they expose a retire function, which the user has to call whenever a node gets unlinked from the data structure. And as an example, after C gets removed, then we have to call retire on it, and this function is responsible for delaying freeing C until after it's not protected by any process. And the way that memory is protected is different for the different schemes, but we can broadly split them into two different categories. there are those schemes that protect individual pointers, for example, hazard pointers and pass the buck. And there are also those that protect entire regions of code. And examples include APOC-based reclamation and read copy update. So in general, the protected pointer approaches end up being slower because protecting a pointer requires doing a memory write followed by a memory fence. And the memory fence is the expensive part, and it's required because you have to make sure the write reaches memory before you dereference the pointer. So on the other hand, the protected region approach is more coarser grained, and you only need a memory fence when you're entering the protected region of code. And this memory fence will protect all pointers that could potentially be accessed in that section of code. But the downside of the protected region approaches is that they could potentially use a lot more memory because the protection is more coarser grained. Okay, so now let's switch over to the concurrent reference counting side. So there has been a lot of work on this topic, but for a long time, it's been considered too slow to be used in practice. However, there has been a lot of work in the last 2 or 3 years. There has been a lot of cool advancements that make it as fast as protected pointer approaches. And we'll focus on one particular paper from PLDI last year on concurrent deferred reference counting. And many of the ideas in this paper are built on top of that. So CDRC addresses two major challenges. The first one is about correctness. And the issue here is that when the reference count of an object is 1, there could be a race between one process trying to increment it, while another process decrements it to 0 and tries to garbage collect the object. So then the problem is that the process incrementing might access an invalid memory location. And the second issue has to do with performance. So if a lot of processes are accessing the same object, then there can be a lot of contention on the reference count. So CDRC solves the first problem by delaying decrements until they no longer race with increments. And to do this, they use a hazard pointer-like interface with 4 operations: acquire, release, retire, and eject. So acquire and release are used to protect the pointer while the increment is happening. And retire and eject are used to delay the decrement. So after you destroy a pointer, instead of decrementing right away, you pass it to retire, and then some later eject operation will return the pointer when it's safe to actually do the decrement. And the nice thing about this approach is that when the object reference count reaches 0, then it's guaranteed that there's no more pending increments on that location, so the object is safe to free right away. Okay, so for the second challenge, to get good performance, it's important to avoid having too much contention on the reference count. And CDRC lets users annotate which pointers are short-lived. And then for these pointers, it doesn't change any reference counts at all. So usually, to dereference a pointer, you have to first acquire it, increment its reference count, and then release it. But for short-lived references, you can just protect it the entire way using acquire and release, and you can safely access it in between. So the way that CDRC implements acquire and release is using an approach similar to hazard pointers. And then the question that motivated this year's PLDI paper is, can we generalize this approach to other manual SMR schemes as well? And then, so for example, maybe we want to use a protected protected region approach like APOC-based reclamation. And then the follow-up question is, will we get all the performance benefits associated with these protected region approaches? And it turns out that the answer to both the questions is yes. So to see how the generalization would work, let's take a look at a more interesting execution of CDRC that has 2 pointers, P1 and P2. So if we were to instead use a protected region approach, then the execution would look more like the bottom diagram. And basically, all the reference count increments has to be done within the protected region. And as an optimization, you can also dereference pointers in the protected region without performing any increments first. And we would expect the bottom diagram to be faster because it requires only one expensive memory barrier when you're entering the protected region, rather than having one on every acquire. So the reference counting approach in this paper basically takes the union of both the diagrams so that it works for both protected region and protected pointer approaches. And depending on which memory reclamation scheme you use to implement it, sometimes the acquire and release might just be no-ops. So we extended the original acquire-retire interface with 4 additional operations. And the first two we've already seen before. And the next one is a custom memory allocation function, which lets you add metadata to the allocated object. For example, a timestamp of when it was created. And this is useful in some memory reclamation techniques. And finally, we also add a try acquire function, which behaves similarly to acquire, except that it can possibly fail. And we need this one because some manual techniques only provide a limited number of guards for protecting pointers. The try acquire function lets you know when you've run out of guards. And in our reference counting algorithm, if this happens, then we fall back to a slow path. So basically in our paper, we saw how to implement this generalized acquire retire interface using a bunch of different manual SMR schemes. And then we saw how to implement concurrent reference counting using generalized acquire retire. And this approach works not just for protected pointer and protected region schemes, but also for hybrids of the two, like interval-based reclamation. And so there's a lot of details that went into these to get these implementations to work, which I won't have time to cover, but the ideas can be found in our paper. And essentially, this approach lets you make a wide range of manual techniques more automatic and easier to use. So we've implemented all the variations of reference counting shown on this slide in C++ and ran an extensive set of experiments on them. But for this presentation, I'll just focus on hazard pointers and epoch-based reclamation to avoid cluttering the graphs too much. So for the graphs here, we applied some different reclamation schemes to a lock-free binary search tree by Natarajan and Mittal. And we measured the overall throughput of the data structure. So higher is better. So the graph on the left represents an update-heavy, a lookup-heavy workload. And the graph on the right represents an update-heavy workload. So both experiments were run on a machine with 72 cores and 144 hyperthreads. So the graphs have two manual schemes, hazard pointers and EBR. And we also benchmarked two reference counting schemes, CDRC, which is currently the fastest reference counting implementation, and RCEBR, which is one of the new algorithms in this paper. And we can see from both experiments that RCEBR ends up performing much better than CDRC, and it approaches the performance of the original EBR scheme. So although we sped up reference counting considerably, it's still a tiny bit slower than the original EBR. But we believe that this performance cost is worth it because reference counting is a lot more automatic and is less prone to errors. So in conclusion, we described an approach for converting manual SMR schemes into reference counting techniques. And we also presented an efficient algorithm for atomic weak pointers, which is useful for writing data structures with reference cycles. We implemented all of these ideas in a C++ library, and it supports an interface that's very similar to atomic third pointers and atomic weak pointers from the C++ standard. So the user of the library doesn't need to know anything about manual SMR or acquire retire, and all of that is just used behind the scenes to implement the library. And that's the end of this presentation. Thank you for listening, and I'd be happy to take any questions.
Can you talk a bit about what practical barriers there might be to the adoption of this technology?
Okay, I see. So practical barriers to the adoption of technology. Let's see. So to use this in practice, we provide around 4 or 5 different pointer types that the user can choose from. So you basically replace the raw pointers in your program with these special like reference counted types. And there's some subtle differences between each of these pointer types. So perhaps just like learning about which situation to use which type could be a practical barrier.
Thanks.
How do you measure like the memory in the experiments? How do you like measure the memory use, and like how do you make sure that thing is actually being freed or not?
Oh, I see. Right. So we have graphs in our paper for memory usage. I didn't show them here. So the way we measured the memory usage is let me try to remember this. Oh, right. So what we did was we paused the execution at a certain point, and we counted the number of we had a custom memory allocator that tracked how much memory was being allocated and deallocated, and we subtracted those two at some point during the execution.